let us now have a look at the structure of the response function. I have written the basics up here. We avoided some prefactors. That doesn't matter right now, but what is important for our subsequent discussion is the fact that we have these commutators in here. This is actually no simple expression. It involves two terms here, because there is a v, the commutator, acting on both sides of the row, so it creates some type of a different state that is composed of two terms. Then we have some evolution of them, and the next step is again applying of a commutator. So out of each of these two terms we make another two terms, and that happens in here too. So altogether we have 8 terms in this trace expression here. Now, what about these evolution superoperators here? So far we have been doing nothing like the open quantum systems theory or whatever. This U still contains, or these U's, they still contain the complete evolution of the system, including, if there would be such division, the relevant and irrelevant degrees of freedom of the system, the bath, electronic degrees of freedom, anything. Basically everything is in here, so we can still write it as if we know the full Hamiltonian. So we can write this thing: U acting, UT acting on an arbitrary operator U, looks like actually U, the normal evolution operator, no superoperator, acting on A from one side, and U dagger acting from the other side. So now if we would write out this U as a commutator, we can also write this V as a commutator. We can also write this U as this series of things. So altogether we can look at this expression as something that kind of sort of rolls out. We will explicitly express all these actions on the way, and we will start, because we are here in spectroscopy, we'll start with some with a system in some initial wave function that corresponds to the electronic ground state, and well, there will be of course other degrees of freedom that well, we will not look at them in the detail, but we will make sure that they are taken into account, at least by the evolution of these things here. Alright, so the row equilibrium in our case would look like the product of the ground state of the electronic degree of freedom, and then here we would have some equilibrium density matrix of the rest of the degrees of freedom. And now on this we have acting of this particular operator, of the transition dipole operator, about which we will assume that so-called Condon approximation is valid. That Condon approximation means that the transition dipole moment does not depend on the degrees of freedom of the bath. So this thing is not actually attacked by V at all. Only this part, only the electronic part of the density matrix is actually changed by acting of this V. So in principle we can start right away to draw a diagram that would allow us to follow this all these actions from right to the left. So we'll start with our G and G. This is the initial point of our diagram, initial state, and now we have a commutator which acts actually once it acts from this side, so once it acts like this, and once it acts with a minus from this side. So if it acts from here, it just means that mu acts on G. This is a transition dipole moment, so there will be a transition into the excited state. So we will denote that excited state E. There can be actually a bunch of excited states here. There's no, but we will treat just one. So when the thing acts from the left, we will denote this in our diagram by a downward arrow, and we will add here this new state EG. The action can of course at the same time also happen from the right, and we will get therefore we will get GE here. So now, from now on, there will be an action of this evolution operator, and the evolution operator action, as I said, it's gonna mean just that this part of the density matrix will evolve, and we will have to go into more details, because now you can imagine that we have, you know, ground state here, excited state here, so the system might be evolving according to, on both sides, according to different Hamiltonians, the, let's say, Bath degrees of freedom for the system in the ground state and the excited state. They might be different. We will discuss all that somewhere else, but now let's ignore it. So we will have the time evolution over T, and the structure of the density matrix is still the same. It looks electronically like this, and then there are also some density matrices or parts describing the Bath. So we will have now another action of the of V on both these states, and they will also correspondingly both lead to either action from the left, which we denoted by the downward arrow, and that is on both of them, or in the action to the right, again on both of them. Alright, so what's gonna happen in our simplified model here? So this action can lead to some new state. Let us stay really with a two-level system, EG. So this action of the transition dipole moment operator from the left can only mean that we go back to G. So here we are back to G, whereas here it can only mean that we go up to E. Here it can only mean that we go to E, so we get to the same element, and here it can again be just GG. Well, how many more operators we have to account for? We have accounted already for this one and for this one, so there will be one more doing the same job. So we will have this, 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 and this, and what's gonna be there? We will have EG. Here we will have GE. Here we will have EG, and there is one row also here. And what about up here? We will have GE. Alright, and now there is an action from the left. There is an action of the last operator, which is just an operator, not super operator, so it acts only from the left, and this brings us back to here back to GG. This brings us to EE. This brings us to GG, and this brings us to EE. So we have four different ways to end. Well, there are actually two different ways to end, but we have four these endings, and now we are making a trace over everything. So let's have a look. There's a trace over this, and that trace is done along the transition, along the system or the electronic degrees of freedom, and also along the Bath degrees of freedom. So this, sorry, there is an error here. This should be G. So this part can, in principle, give us easily this one also, and this one also, and this one also. They can give us non-zero trace, because we are at the diagonal of the density matrix. So this is fine. This we can live with. And now we have these 8 contributions that we can now actually design, or which we can describe as pathways through these diagrams. Now, whenever there is an action of the transition dipole operator from the right, so there's this this arrow, there was a minus sign involved in it. So actually everywhere here we should have a minus sign. So let's have a look how we can get from here, from the initial point to the end point, to get a non-zero contribution in a unique way. So there has to be, as we said, there have to be 8 different ways, and let us see which they are. But before we do that, let's also notice one thing. The expressions that we would get, we should not, let's say, have that really in full detail, but let's say if we would run like this, or if we would run like this, we can see that these terms here, they are always complex conjugated to each other, or Hermite conjugated to each other. Actually, we would have 2 pathways, those that are mirror images with respect to this central line here, that would be under the trace. They would be they would be Hermite conjugated. So there would be something like a trace, and there is a trace of a dagger. Well, in fact, they are not. In such case, the things are not equal, but they are equal when we take complex conjugation over everything. So we would have apparently pathways that are mirror images of each other, and those things would have a star. They would be complex conjugated. And because every time we take a pathway, there has to be a mirror image of that pathway, we would have four pathways that are unique, and 4 pathways that are the complex conjugated pathways to them. Now let us let's say select for our as our basis pathways these let's select those that have the plus sign. So we are looking for overall plus sign, and those are those things that do not have odd number of the minuses. It's very simple actually. So one that is certainly positive is this one down here. So let's write this one. It's this pathway. I'll just write its shape. Then let's say plus, minus, minus, plus. So this would be another shape like this. Then let's say this, and this. That's not as far as I can tell, this is not a complex conjugation of anything that we had so far. So 2 and 1 down. And then we have to have one more with just, well, which one is it? Okay, that would have to be, let's say, here and here again. Yeah, so it's gonna be the one with 1 down 1. 1 down 1. That's it. So that these are the four different pathways, and in the next video we will go into the expressions for them, the details, and let's say we will try to express them for 2-level system in somewhat more details than so far.